You're probably familiar with the following. 13.8 billion years ago, the Big Bang led to stars and galaxies, which led to planets and life, and eventually to you and me. But there's a glaring gap in this chronicle, an aperture so big solving it would shake our knowledge of reality. According to Stefan Ulmer, a physicist at the RAICN and CERN who led the Baryon anti-Baryon symmetry experiment at the European Council for Nuclear Research, if we plug in principle, the best physics theories, we would need to conclude that the universe as we observe it cannot exist. But here we are playing Wordle and paying taxes, so either our laws of physics are wrong or we're missing massive pieces of the metaphysical puzzle. Join us as we dig deep into why shouldn't the universe exist. Let's start at the beginning with an unimaginable number, 10 to 10 to the 123. It's called the Penrose number, an equation of a miracle, and its simplicity in appearance belies the impossibility that it represents. These are the odds in which the likelihood of the universe coming into existence in a way that would develop and support life is nearly mathematically impossible. To put that figure in perspective, at the beginning, the Big Bang is an implausible and unlikely event with a 1 in 10 to the 10 to the 1 and 123 chance. Mathematician and physicist Roger Penrose formulated this equation, and by all accounts, it is sound and fully checks out theoretically. Penrose won a Nobel Prize and was a close associate of Stephen Hawking, so his credentials are unmatched. But to better understand what this number represents, we need to context how Penrose's number was conceived. You're probably familiar with the Big Bang Theory. The Big Bang Theory, as told, is the leading explanation about how the universe began. At its simplest, it says the universe as we know it started with a small singularity, then inflated over the next 13.8 billion years to the cosmos that we know today. And according to this premier theory, the universe came into existence as a result of a set of very specific, precise conditions and occurrences. One of those conditions was something called initial entropy. Entropy is the degree of thermodynamic disorder in a closed system like the universe. According to the second law of thermodynamics, any isolated system must evolve from states of low entropy to states of higher entropy. Disorder always increases. If you start with a bunch of atoms all crowded into one corner of a box, they will naturally evolve to a state with atoms spread uniformly around the box. They have thus moved from a highly ordered, low-entropy state to a state of maximum disorder and maximum entropy. The important thing about maximum entropy is that once the state is reached, evolution stops. Individual atoms continue to bounce around, but the macroscopic state of the box ceases to change. In a sense, time and its direction no longer matter. The past looks exactly like the future, so you cannot tell them apart anymore. Bring this idea to the universe as a whole, and you will quickly see the problem. Since the universe is everything that exists, it is kind of like that box. The second law of thermodynamics says the entropy of the universe can only increase until it reaches a maximum. So, the universe must be running down, and it must be heading toward an eventual heat death, where entropy has maximized and no more work can be extracted. In that final equilibrium, there will be no more change and no arrow of time pointing from the past into the future. But that is not the state we are in now. The universe is clearly still evolving. Stars are burning up their nuclear fuel, releasing energy and generating entropy. That must mean the entropy of the universe has not reached its maximum. Based on this, we can conclude that the entropy of the universe must have been much lower in the past, and that is where the problem really lies. Why was the entropy of the universe lower in the past? This question is not new. The founders of modern statistical mechanics and thermodynamics were aware of the issue and discussed it at length even before the rise of modern cosmology. But once scientists developed the Big Bang model of the universe, the problem got more acute. The so-called classic Big Bang, the first version of our standard model of cosmology, says the universe began in a hot, dense state undergoing expansion. The modern version of the standard model adds a period of extreme expansion to this story, a very brief, very early period referred to as inflation. For both the classic and modern standard models, the critical question about the past is the initial condition of the Big Bang, that state under which your model begins its evolution. Solution? It turns out that if you pick an initial condition at random, you are much more likely to find one with high entropy than one with low entropy. After all, there are many more ways to arrange a system's components in a disordered fashion than in an ordered one. Based on probability alone, then, the universe should have started in a state that was either already in equilibrium or close to it. That would leave little room for cosmic evolution. The universe would just sit there like our box of atoms in equilibrium. It would experience no change and no time running from the past into the future. Somehow, our universe must have avoided all those high entropy states and started in a very unlikely, very low entropy state. In other words, those initial entropy conditions had to be absolutely perfect in order for the universe to develop as it did. Physicists and philosophers call this the past hypothesis. But what makes this hypothesis correct? Why did the universe begin in such an unlikely state that allowed us to emerge? This is the context in which Penrose enters the discussion. Penrose wondered about these questions. What initial entropy conditions had to have existed in order for the universe to have been created in accordance with the Big Bang theory, and for that universe to then ultimately be supportive of life coming into existence randomly? What are the odds that those exact conditions could have existed at the time of the Big Bang? The Penrose number is his scientifically based and calculated estimate of those odds. According to Penrose, the odds against such an occurrence were on the order of 10 to the 10 to the 123. As you probably already surmised, those odds are infinitesimally nanoscopic. In fact, the human mind cannot even grasp just how tiny those odds are. To help provide some perspective on just how small those odds are, you can get a grasp of somewhat how big the number is by learning more about how exponents and specifically how powers of 10 work. 10 to the 123 is written as a 1 followed by 123 zeros. That's already an insanely big number, but then it gets way worse, because 10 to 10 to the 123 is 1 followed by 10 to the 123 zeros. 10 to the 123 is greater than the total number of atoms, which is thought to be 10 to the 79 believed to exist in the entire universe. And in Penrose's book The Emperor's New Mind, concerning computers, minds, and the laws of physics, Penrose wrote this: one could not possibly even write the number down in full in the ordinary denary decimal notation. It would be 1 followed by 10 to the power of 123 successive zeros. Even if we were to write a 0 on each separate proton and on each separate neutron in the entire universe, and we could throw in all the other particles for good measure, we would fall far short of writing down the figure needed. Ron Mazur, a former lecturer at Tulane University, offered us a more understandable explanation. According to Ron, the odds of you winning a million sweepstakes 200 times per day for 41 straight days would be 10 to the 10 to the 5. That's crazy, but that is not even close to the odds against one of the foundational assumptions of the Big Bang theory, as expressed by the Penrose number. My brain almost breaks trying to understand the magnitude of those odds. It's put simply too large, too complex for my limited understanding. But this impossible number is the only factor that challenged our understanding among the army of scientists looking for the puzzle pieces missing from the picture of the very early universe. Scientists like Stephen Ulmer have spent years studying the seed of our universe's existential crisis, antimatter. But what is antimatter? Everything from the sun to the device you're reading this article on is made up of the normal matter we know and love, composed of atoms built with positive protons and negative electrons. The Big Bang gave rise to all this matter, and the rest is literally history. Here's the weird part: our universe also holds a tiny amount of antimatter, composed of atoms built with negative protons and positive electrons. It's like the Big Bang's rebel child. These two also have a rift. When they come into contact, they totally annihilate one another because of their opposite charges. Even when scientists create antimatter for experiments, the zippy particles must remain in a vacuum because an antimatter particle in a normal matter environment would immediately go poof. This incompatibility dominoes down to a huge existential problem, and it's not just that we can't meet our antimatter counterparts someday without basically exploding. Physicists use two main frameworks in explaining particle behavior: the standard model of particle physics, and relativistic quantum field theory. Each is super solid in its own right, and combining them leads to a perplexing outcome. Matter and its arch-nemesis are two sides of the same coin. According to Ulmer, the architecture of space and time basically implies that matter and antimatter are, in principle, exactly symmetric. This means they have the same masses, they have opposite charges, opposite magnetic moments, and so on and so forth. If that's true, the Big Bang should have had a 50-50 chance of forming either one, and had a 50-50 distribution happened, antimatter and matter should have completely destroyed one another. Remember the rift was such a particle war? The universe wouldn't have any matter, space wouldn't hold a sun or an earth would surely lack humanity. Only a leftover sort of energy would have lingered after the battle. But the sun, earth, and humans exist for some reason. The universe exhibits several orders of magnitude more matter than antimatter, a cosmic riddle known as baryon asymmetry, the namesake of Ulmer's laboratory. Did Big Bang generated antimatter vanish? Was there never any to begin with? The answer Ulmer gave was simple: we do not understand the origin of matter and antimatter asymmetry. But because the standard model's prediction of a 50-50 matter-type distribution relies on the particles being exactly symmetrical, the mystery may finally be solved if we find a way to breach the presumed parallel. As Ulmer said, if, let's say, the proton would be a bit heavier than the antiproton, that would immediately explain why there is more matter than antimatter. That would pretty much elucidate why the universe exists. Let's return to Ulmer's study results. Both matter and antimatter respond to gravity the same way, ruling out some options on the ledger of possible symmetry violations. Ulmer's experiment began with a fascinating device called a penning trap, a small metal contraption that detects a particle's cyclotron frequency, or the frequency at which something moves in a magnetic field. The researchers placed a lab-produced antiproton inside and measured its cyclotron frequency. Then popped in a negatively charged hydrogen ion and measured the same parameter. Ulmer used a negatively charged hydrogen ion or atom with 1 proton and 2 electrons as a normal matter representative because it matched the antiproton's negative charge. It's easiest to think of the experiment in terms of music. The penning trap's pickup system, in Ulmer's own words, is akin to what's in an electric guitar. It's, in that sense, a very musical experiment. The frequency range is a bit different, but we are listening to the sound of what does not exist in the universe with our current ability to listen. Matter and antimatter sound identical, the particles play the same melody, if you will, which also means they have the same music notes. AKA, these particles' cyclotron frequencies were the same, as were many of their resulting properties, such as charge-to-mass ratio. All of these similarities are now eliminated from the list of possible matter-antimatter symmetry violations. But the researchers' ultimate goal was to use their cyclotron frequency data and see whether the antimatter song changes alongside adjustments in a gravitational field, specifically whether Einstein's weak equivalence principle, true for normal matter, works on antimatter. Einstein's principle states that any object in a gravitational field behaves independently of its intrinsic properties. For instance, a piano and a feather would fall to Earth with the same acceleration in the absence of external forces, such as wind. Intuitively, we might assume antimatter's opposite charges would force it to fall up or at least have some variation in behavior. For this facet of the experiment, Ulmer took advantage of some cosmic lab equipment, the Earth and the Sun. As the Earth is orbiting around the Sun in an elliptical orbit, the gravitational potential in our laboratory changes as a function of time. So, he and his research team measured the cyclotron frequencies, aka the melodies, of both the antiproton and negative hydrogen ions at different points in time. After 24,000 comparisons, they concluded both particle types reacted the same with very, very high certainty. Voila, Einstein's principle works on antimatter. It does not, in fact, fall upward. So, if we find something unexpected in these experiments, this would change our fundamental understanding of the laws of nature. For argument's sake, let's suppose someone finally finds a discrepancy between antimatter and matter. What might that mean for us? Violating matter-antimatter symmetry would mean violating a larger phenomenon called CPT invariance. C stands for charge, P for parity, and T for time. In a nutshell, the rule states if any of these things were reversed, the universe would fundamentally remain the same. If time went backward instead of forward, if everything was left-handed instead of right-handed, and, you guessed it, if all matter had the opposite charge, the world wouldn't change. If we were to find antimatter isn't the same as normal matter, C would be violated. And if CPT invariance is violated, then causality, scientists say, may no longer hold. I think this would maybe lead to a more philosophical change in our thinking, Ulmer said, comparable to what happened in the 1920s when